again, our driving activity is going to be. Ooh, ready for this analogy? The driving activity is going to be the activity. It's going to be the concept that the vehicle that propels us into the whole idea of integration. All right. The most basic example I gave was you drive 50 miles per hour for 2 hours. You went 50 miles an hour for 2 hours. You went 100 miles. The area under a constant, it's a rectangle. The area under a constant is a rectangle. The area under a linear function, depending on where you start and stop, it could be a triangle. But if you move it up a bit, it could be a trapezoid. It's a geometric shape. But the area still means what? An area under a velocity curve, miles per hour curve. Distance, miles. So what's this saying? If you have a height of c, if your function is a constant, we have this new notation we're using now. If your height is constant and you're going from a to b, isn't your base b minus a and your height is c? We don't need calculus for that. It's c times b minus a. It's base times height. It's a rectangle. All right, cool.
Why does c have to be on the interval AB?
What do you mean?
When it says where c is a constant on the interval AB, why does it have to be within a and b? Why can't it be higher than b or lower than a?
Well, c is a y value, so it's technically it's constant on the interval from a to b. It's not a c value within a to b. What if c is negative? It's a negative area, right? Now, we can go back and forth on whether area can be negative or not, right? Some people might say it's an area of c times b minus a that has a signed value of a negative. Whatever. All right. Do you understand this? Now let's talk about your driving activity. All right. You were supposed to do LRAM 30 and RRAM 30. So we had 10 seconds, 10-second intervals. Let's pretend that our velocity was 40 and then 30 and then 15 and then 35 and then 50. All right. LRAM LRAM 30 should be, well, aren't my bases 10-second intervals? I told you to convert them into miles, or sorry, hours. 10 seconds is 1 over you say 360? 10 seconds. 10 seconds? 10 divided by 60 for a minute, right? Oh, you're just saying, okay, some of you who didn't reduce, it'd be 10 over what? 3,600, so 1 over 360. Okay with that? All right. I almost tricked myself there for a minute. All right, 1/360th of an hour. So base times, do I use 40 for LRAM? Do I ignore 40 for LRAM? Use it. Plus 1/360th times 30 plus ... I hope you didn't type that in, because can't we factor out a 1/360th out of all the terms and then add up? I mean, it's just simple math. Every term has a factor of 1 over 360. Factor it out. Then you add up 40 plus 30 plus 15 plus 35 plus 50 plus ... plus v sub n minus 1. Okay? V sub 29. Not V sub 30. It's not a right Riemann sum. We're going to ignore the last input. Do you agree? What does LRAM? Sorry, what does RRAM 30 look like? 1/360th times, what's the first term? 30 plus 15 plus 35 plus 50 plus ... plus V sub n. The last term. We're going to include the last term. You guys, as I walked around, you guys did really well. There weren't many calculation issues. Usually every year I have to kind of address, oh, you missed this or missed that. Help me out. I saw your calculations. Your LRAM and RRAMs weren't too far off. Okay? What would cause them to be far off if your first velocity and last one were quite a bit different? Because on one of them you're going to include that low value, or vice versa, right? And ignore the last one. So if they were pretty close, your calculations are going to be pretty close. What's next? How close was your approximation to what your odometer said? How many of you got within 1/10 of a mile? 1/10 of a mile. If you were to average your LRAM and your RRAM and then look at your odometer, how many of you got within 2/10 of a mile? 3/10 of a mile. Okay, those of you who got within 1/10, you can keep your hands up. So, within 3/10, within half a mile. Okay, thanks. That's kind of good. I mean, that's pretty good, isn't it? Like, would you have expected that from just every 10 seconds calculating and then a simple calculation of just space-time sites? It's kind of a neat application of it. Do you understand what's going on there? Now, as I looked around, I wanted to talk to the whole group about this. When you go to graph these, they should just be data points, all right? They should just be, on their own, they're data points. We don't connect them. We don't draw horizontal lines between them. This is a discrete set of data, all right? It's not continuous. Now, in reality, it's continuous, but our data set was discrete. There's a bunch of dots. When you go to do LRAM, that's when you could draw in the rectangle, LRAM. All right, or RRAM and so forth. All right. So the area under the velocity curve, is your distance, as long as your velocity is positive. Do you get that? How could we make this more accurate? Say next year I want to say, no, I want everybody to get within 1/10 of a mile. How do we get more accurate? More time, yeah. More calculations. Every 5 seconds. Every 2 seconds. All right? And you get more and more and more accurate. That's the idea that we took from yesterday into today, where we now are doing definite integrals that take infinitely many calculations into account. All right? Questions on that? All right, we'll come back to that driving activity as a concept. But if you did it pretty well, and your variations in your speeds weren't a ton, then you probably got pretty close. All right, we're going to finish up 5.2. But first, let's talk about the homework. Your homework was 3, 6, 9 through 18 multiples of 3. I had to do math to do your homework, huh? 3 was just rewrite it as a definite integral. 6, you should have gotten. 6 was an even, so I'll write that out. Integral from negative pi to pi. Sine cubed x dx. Good with that. Number 9, you should have gotten negative 480. You guys okay with that? Without plugging in the calculator. How'd you do that? Did you graph it? Or just think, hey, that's constant. That's constant. Base. It was 0 to 3. So it's 3 units wide. Negative 160 units tall. The area is negative 480. Good? And then, was it 12 through 18 multiples of 3?
Yes.
What'd you get for 12? 2, 4? Do you understand how to do that? I need to see it. I see a yes. All right. 12. It was the integral from radical 2 to radical 18. Area under radical 2 dr. What does that dr tell me? The independent axis is not x, it is r. I don't know what the vertical axis is called. They didn't tell me that information. Okay, well, here's your visual. Here's your r-axis. What's radical 2? Well, here's 1. Here's 2. Radical 2 is, I don't know why I dashed it, whatever. But this is, I'll just say y equals radical 2. 1.41-ish. All right? Now, where am I calculating the area from and to? Well, radical 2, from radical 2 to radical 18. Do you guys see the rectangle formed? Base, radical 18 minus radical 2, times the height, radical 2. What's radical 2 times radical 18? Radical 36, which is minus radical 2 times radical 2. 2. Area is 4. Make sense? That's how I want you to do it. If it's a constant, you should just think it's a rectangle. No problems. That was 12. 15, did you recognize it was a semicircle? It said use the graph of the integrand. Integrand is the function. And areas to calculate. Did you recognize that was a semicircle? We've done that one quite a bit this year. It was the square root of 9 minus x squared. What's the radius? Good. 3. Can you guys recognize that's a circle? Semicircle? It's not plus or minus, so it's just the top half. What if it's... Okay. You guys have to recognize this. If I put it in standard form, I would square both sides and add x squared over. X squared plus y squared equals 9. That's if it was a full circle. Standard form of circle. So this is not plus or minus. It's just the top half. And so it's the area is half of a pi r squared. Half pi times 3 squared, which is 9 pi over 2. We good? And 18. It was 1 minus absolute value of x was the integrand. Absolute value of x. This one. I am blanking. Wow, that's embarrassing. All right. Negative 1 and 1. Did you guys graph that without a calculator? Absolute value of x would be this, right? So negative absolute value of x is that, and then it's negative absolute value of x plus 1. And it's going from negative 1 to 1. Now, be careful here. Can I do an example of what would happen if I went from negative 3 to 3? This is not this problem. Can you visualize what the integral would be calculating if you went from negative 3 to 3? Can you visualize which areas you're finding? It's this, and then this, and then this. It's the area between the function and the x-axis. Can you see it? Okay. But we're not doing that. We are doing from negative 1 to 1. So what is the x-intercept here? Did you get negative 1? Yes? What's the x-intercept here? So we're actually just calculating that positive triangular area. Area of a triangle. See, these are all geometric shapes. Area of the triangle is 1/2. What's the base? From negative 1 to 1? 2 times the height. Did you get 1? No calculus involved. All right, we did not do any calculus. That was only practicing. Oh, you're asking me to find area? Okay, I'll use a geometric formula to find the area of that region. No calculus involved other than the notation. Hopefully today we will make a connection with the calculus of it. Real quick, I showed you yesterday in the calculator how to do that. It's the templates button and it's the definite integral button there. All right, we will be using that quite a bit coming up. Questions on 5.2? All right, I have a really valuable activity for you guys. It's a group activity. And it's just a packet, it's just a worksheet, all right? But I pulled it from another book. I've used it for years. And if you walk through it properly, I'll say it again. If you walk through it properly, you should start to understand our conversation more about from yesterday, where Cole mentioned antiderivatives. I don't think many of us in here truly grasp what was happening when we talked about antiderivatives. Do you? Be honest with me. How does an antiderivative find area? How many of you completely understand it? But can you at least understand the idea of the area has to do with an antiderivative function? Why? Again, velocity, moving to the right. Area under what's the area under my meters per second curve? Meters. Oh, okay, you just traveled 3 meters to the right. Velocity. Meters is a position question. Antiderivative, not acceleration, position. Okay, my velocity is negative. Area under my velocity curve would have been meters. That's a position question. It has to do with this antiderivative function. Can you at least understand that aspect of it? Hopefully with this activity, you'll start to step into that understanding of how they're connected. All right? I'm going to give some introduction once you have the worksheet in front of you. But you're going to group up into a couple people. I don't care. 3, 4, 2. Hi. People. All right. You will get more out of this if you have a good conversation with each other. So don't go rogue, all right? So number one, consider the constant function f of t equals 4. Do you notice how the lower bound is 1 and the upper bound is x? That's because that upper bound is going to be sliding to the right or to the left. Can you see that? The part A says, using geometry, compute the integral from 1 to 2. All right, if you're going from 1 to 2, what's the base? 1, height, 4, area, 4. Done. Then part B, you're going to go from 1 to 3. Okay, x is now slid to the right. Then 1 to 4. Okay, slid to the right a little bit more. And then part C. Using your answers to parts A and B as a guide, compute the integral from 1 to x. What's the base going to be now from 1 to x? X minus 1. Very good. Parentheses, x minus 1. What's the height? 4. Go ahead and distribute. Distribute the 4. And that is going to be called, in part B, they're going to call that a of x. That is now an area function. And you can repeat that. This is so important. Cannot emphasize this enough. A of x is an area function. What's its input? A of x. What's its input? X. And what does x mean in the context of this problem? What does x mean? What was x in our picture? The upper bound. Okay, add up area, add up area, add up area, add up area, stop. Wasn't x the stop sign? X was 3, x was 4. Oh, I input x, I output area. It's an area function. A of x. Pause after you get that a of x function and compare that a of x function to the f of t function, and then move on. That's my guide. It's going to keep building. Okay, then you're going to get a new graph in part 2, and then you're going to get a new graph. Please work together. Please have good conversation. This can be very helpful for you guys to discover the relationship here. All right, enjoy. Oh, I forgot the joke of the day. England doesn't have a kidney bank, but it does have a liver. I like that.